In this lesson, we're going to get an introduction to power series. So a power series is any infinite series that has increasing powers of x. So for example, this first term is just a constant, so that's x to the 0 power, and then we have x to the first power, x to the second power, and so on. There can be any constants in front of those as long as we have increasing powers of x. So x to the 0, x to the first, x to the second, x to the third, and so on, going on to x to the nth power and continuing on forever. So that's an example of a power series about x equals 0. And what that means is we're eventually going to try to find all the x values that make this series converge. Now, about x equals 0 means that if we plug in x equals 0, then this series is obviously going to converge, because if x is 0, then all these terms would become 0 except for the first term, so the series would converge to C0, C sub 0. And so we're going to look and see, does it converge at other x values? Okay. Another form for a power series about x equals a is the same idea, but we have some factor, some linear factor x minus a with increasing powers. So again, we have a constant term, so that's x minus a to the 0 power, and then we have x minus a to the first power here, and x minus a to the second power. Next term would be x minus a to the third power, and so on and so on. The general term is some constant times x minus a to the nth power, and again, that continues on forever. The c's are all just constants, so those are the coefficients of the x minus a terms. And so again, if a was 0, then we would just get this series. And so this power series will also converge when x equals a, because if x equals a, then all of these terms will become 0, and so it's going to converge again to c sub 0 or c naught. And so we're going to try to figure out, are there other x values where this power series converges? So every power series will converge at least at x equals a, and we're going to look for intervals of other values where it converges. So let's take a look at this simple power series. This, if we plug in 0 for n, that would be x to the 0 power, which is just 1. If we plug in 1, we get x to the first. If we plug in 2 for n, we get x squared, x cubed, and so on, going on forever, x to the n, continuing on forever. So that's a very simple power series. And that would be a power series about x equals 0. Okay, now we want to know, for what values does this series converge or diverge? And so since this is a geometric series, this is geometric with common ratio x. To get from one term to the next, all we're doing is multiplying by x. And so we discovered earlier that all geometric series will converge. Remember, an infinite geometric series converges as long as the absolute value of r is less than 1, which is the same thing as saying that r is in between -1 and 1. And so since this series has a common ratio of x, that means x has to be in between -1 and 1. And so we say this series converges for x on the interval from -1 to +1, and diverges for all other values. So this is interval notation from -1 to 1, so it's parentheses because it's not including the endpoints. We know that if r equals 1 or -1, then the series will diverge. And so that's generally what we're going to be looking at for all the power series we look at today, is where is the interval where it converges and diverges. For example 1, we're going to do 4 different things for each problem. We're going to find where does it converge absolutely, where does it converge conditionally, state the radius of convergence, and the 4th thing is to find the interval of convergence. And so in this first example, we see by the hint that this is a geometric series. If we expand this, we'll see that. If we plug in 0 for n, we would get 1. No, I'm sorry. If we plug in 0 for n, we would get negative 3/2. And then if we plug in 1 for n, we would get plus 9/4 x minus 4 to the first power, and then minus 27/8 x minus 4 to the second power, and so on, going on forever. And so we can see that to get from one term to the next, we're multiplying by negative 3/2 and x minus 4. And we decided in a previous chapter that a geometric series will converge whenever the common ratio will converge absolutely whenever the common ratio is in between -1 and 1. That's true for all geometric series. They'll converge absolutely when the common ratio is between -1 and 1, and not including -1 and 1. And so we put negative 3/2 x minus 4 in between -1 and 1 and solve for x. So first I would multiply everything by negative 2/3. So this is going to become positive 2/3. The inequality would change directions whenever we multiply by a negative number. And then we're going to have x minus 4, and then this inequality changes direction as well. And here we have negative 2/3. So this can be rewritten as negative 2/3 is less than x minus 4 is less than positive 2/3. And then we can add 4 to all 3 parts, and we get, let's see, this is 12/3 minus 2/3 is positive 10/3. It's less than x is less than, here we have 12/3 plus 2/3 is 14/3. And so we can say this series converges absolutely when x is on the interval from 10/3 to 14/3. Geometric series don't converge conditionally anywhere, so converges conditionally nowhere. And this is also our interval of convergence. From 10/3 to 14/3. And then the radius of convergence, what that means is from the center of this interval, how far can we go in each direction? So if you think about the radius of a circle, you have a diameter, and if you put a point right at the middle, half of that is your radius. And so if we do the same thing on the number line, if we go from 10/3 to 14/3, if we put a point right in the middle, how far can we go in each direction? And so the distance from 10/3 to 14/3 is 4/3. So that's like our diameter. So that means our radius is 2/3. So if we put ourselves right at the middle, that would be 12 thirds, we can go 2/3 in each direction. We can go 2/3 to the left, 2/3 to the right. You can also think about a circle going through those 2 points, and the radius of that circle would be 2/3. So we say our radius of convergence is 2/3. Okay, example B. This time we're going to use the ratio test to find out when this converges. Remember we said when we apply the ratio test, if L is less than 1, then it's going to converge. Converges when L is less than 1, and when L equals 1, it's inconclusive. So we're going to look at that situation when L equals 1. We're going to look at those values individually. Okay, so let's first find out when L is less than 1. And so if we use the ratio test, L is equal to the limit as n approaches infinity of, remember in the denominator we just put this expression, that's a sub n, so that's going to be x to the 2n minus 1 over 2n plus 1. And then in the numerator we're going to put the same expression, but we're going to replace all the n's with n plus 1. So then this is going to be x to the 2n plus 1, because 2 times n plus 1 minus 1, that's 2n plus 2 minus 1 is 2n plus 1. And so x to the 2n plus 1 over 2n plus 3, because 2 times n plus 1 is 2n plus 2 plus 1, or 2n plus 3. And so now we want to evaluate that limit, and we can do that more easily if we flip the denominator and change it to multiplication. So then that's going to be x to the 2n plus 1 over x to the 2n plus, 2n minus 1 in the denominator. And then 2n plus 1 is going to be on top of 2n plus 3. And this, when x goes to infinity, this is just going to approach 1. And then we're left with the limit as n approaches infinity of, let's see, if we simplify this expression, that just becomes x to the difference between the exponents is 2, so that's just x squared. And so L is equal to x squared. Notice there's no n in that anymore, so it doesn't matter what n is approaching. L is equal to x squared. And so we want x squared. In order to satisfy this, x squared needs to be less than 1. So if you think about numbers that you can square that have an answer less than 1, that's numbers in between -1 and +1. So if we pick any numbers in here and square them, we're going to get answers that are less than 1. And anything that passes the ratio test converges absolutely. So this converges absolutely for x in between -1 and 1. And so now what we need to do is we need to investigate the endpoints. And so does it converge at -1? Does it converge at +1? Because those are the values that make L equal to 1, and the ratio test is inconclusive, so it might converge at those endpoints. Let's look at those individually. So our endpoint analysis, we're first going to look at x equals -1. So we take our original sum and we replace the x with -1. And so now that's going to be the sum from n equals 0 to infinity. If we plug in x equals -1, we'd have -1 to the 2n minus 1, which is always odd, and then over 2n plus 1. And since that's always odd, that's the same as -1 over 2n plus 1. And that diverges. You can show that a variety of ways. You could use the integral test. You could use the limit comparison test and compare it to 1 over n. Remember, 1 over n diverges because of the p-series test, p equals 1. And so you could show that this series diverges either by the integral test or by the limit comparison test. So it diverges at that endpoint. Now let's look at what happens when we plug in +1. That's going to be the sum from n equals 0 to infinity. If we replace x with +1, we're just always going to get a +1 on top over 2n plus 1. This also diverges by the for the same reasons, by the integral test or by the limit comparison test. Okay, so it diverges at both endpoints, so that means it's not going to converge conditionally anywhere. And the radius of convergence, so let me write our interval first. So our interval of convergence is from -1 to 1, we said, not including the endpoints. And so that means our radius is half the length of that interval. So the distance from -1 to +1 is 2, and so the radius is half of that, 1. You can also look here. If you put a point right at the middle, that would be 0, and we can go 1 unit to the right and 1 unit to the left. And so our radius is 1. Okay, so I'd like you to go ahead and try example C. So pause your video, try out example C, and make sure you've done all 4 of the parts. Where does it converge absolutely? Where does it converge conditionally? We said it converges, this one converged absolutely here. Where does it converge conditionally? What is the interval of convergence? And what is the radius of convergence? So make sure you've answered all 4 of those questions for part C. After you've done that, then go ahead and press play and compare your solution to mine. Okay, so I'm going to go ahead and use the ratio test for this one again. L equals the limit as n approaches infinity of n plus 1 x to the n plus 1 over 4 to the n plus 1 n squared plus 2n plus 2 over n x to the n over 4 to the n squared plus 1. And so when I flip the denominator and multiply, we end up, and if we match up all the corresponding pieces, we end up with n plus 1 over n, x to the n plus 1 over x to the n, 4 to the n over 4 to the n plus 1, and n squared plus 1 over n squared plus 2n plus 2. As n approaches infinity, this is going to approach 1. This is going to be x to the first power. This is going to be 1 over 4. And this is going to approach 1. So we just end up with L equals x over 4. We know that the series converges absolutely when it passes the ratio test. So that means since L equals x over 4, and we want L to be less than 1, we want, in order for the absolute value of x minus 4 to be less than 1, then it needs to be in between -1 and 1. Multiply everything by 4. And x is in between -4 and +4. So we know it converges absolutely on this interval. Okay, so now we need to test the endpoints. When x equals -4, our sum becomes n times -4 to the n over 4 to the n squared plus 1. So then that is, if we put -4 to the n over 4 to the n, that's the same as -1 to the n over n squared plus 1. This is an alternating series. And this, as n goes to infinity, this is going to approach 0. So remember, when we have, by the alternating series test, when we have an alternating series with the terms approaching 0, then it's going to converge. So we'll say at x equals -4, the series is going to converge. It converges by the alternating series test. Now we'll take a look at it at x equals +4. So when x equals +4, our sum becomes 4 +4 to the n over +4 to the n squared plus 1. Sorry, this is an n. And then 4 to the n over 4 to the n just becomes 1, and now we have n over n squared plus 1. This series diverges. The easiest way to show that is by limit comparison. Or you could use the integral test. So it does diverge because since n over n squared is the same as 1 over n, we'd want to compare to 1 over n. So we'd look at the limit as n approaches infinity of, let's do 1 over n divided by n over n squared plus 1. And that is, we're just looking for this to be equal to a constant. As long as it's a non-zero constant, then we can use the limit comparison test. And so this is going to be n squared plus 1 over n squared. If we take the limit as n approaches infinity, n squared over n squared is 1. So this limit is going to equal 1, which means we can use the limit comparison test. So at the right endpoint, it diverges. At the left endpoint, it converges conditionally, because if we take this series and put absolute value around it, it's going to diverge, because if we put absolute value around it, it's just going to become this, which we said diverges. So it converges at the left endpoint, but diverges at the right endpoint. So we can say it converges the original series converges conditionally at x equals -4. Okay, so then our interval of convergence is, we said it converges at -4, but diverges at +4. So that's going to be our interval, interval of convergence. And the radius then of convergence is 4, because think about this on a number line from -4 to +4. That's a distance of 8. So that means we can go from 0, we can go 4 in that direction and 4 in that direction. So our radius is 4. And so I think we answered all the questions. It converges absolutely here. It converges conditionally only at x equals -4. This is our interval of convergence, and this is our radius of convergence. Okay, again, pause your video and try example D. Okay, so for example D, we have, using the ratio test, L equals the limit as n approaches infinity of x to the 3n plus 2 over n plus 1 factorial divided by x to the 3n minus 1 over n factorial. That's the limit as n approaches infinity of x to the 3n plus 2 over x to the 3n minus 1 and n factorial over n plus 1 factorial. And this simplifies. The difference in the exponents here and here is 3, so we get x cubed. And n factorial over n plus 1 factorial is 1 over n plus 1. We can see that because if you take a number like 6 factorial over 7 factorial, that's 6 times 5 times 4 times 3 times 2 times 1. 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. Those all cancel with those, and so we just end up with 1/7. So that's what we have here, is just 1 over the biggest number in the denominator. And now as n approaches infinity, remember x we're just thinking of as a constant in this case. It's n that's growing to infinity. So we have a fraction. We have this fraction x cubed over n plus 1, and the denominator is growing infinitely large. So that's going to make that fraction approach 0 no matter what x is. And so L equals 0, which is less than 1 for all x values. And so that means this series, the original series, converges absolutely for all real x, which means it doesn't converge conditionally anywhere. The interval of convergence is -infinity to infinity, and so that means our radius of convergence is infinite. I'll work through one more example where we have to test the endpoints with this one example E. And so setting it up with the ratio test, we get L is equal to the limit as n approaches infinity. By the way, you'll notice that in almost all these examples, the ratio test is going to help us find the interval of convergence. And even the first example that we did where we used the geometric series, we could have done the ratio test for that one as well. And so we have the limit as n approaches infinity of x to the n plus 1 over n plus 1 to the 3 halves, 3 to the n plus 1, so that's our numerator, over x to the n to the 3 halves, 3 to the n. And so then that is x to the n plus 1 over x to the n plus 1 to the 3 halves over n to the 3 halves. And actually that's the other way around. The n to the 3 halves goes to the top. N plus 1 to the 3 halves is on the bottom. And then 3 to the n goes on top of 3 to the n plus 1. And so this is equal to the limit as n approaches infinity of x. This all simplifies to just be x to the first power. This we can rewrite as n over n plus 1 to the 3 halves, because both the top and the bottom are raised to the 3 halves power. And then this simplifies to 1/3. This expression will approach 1 because n over n plus 1 approaches 1, and 1 to the 3 halves power is 1. So we just simply get L equals the absolute value of x over 3. So L equals x over 3, absolute value of x over 3. So this series will converge absolutely. Remember, we said anything that passes the ratio test converges absolutely. So this series will converge absolutely when x over 3 is in between -1 and 1, which means x has to be in between -3 and 3. So it converges absolutely for that interval. And so now we want to test the endpoints. So if we try x equals -3, the sum becomes -3 to the n over n to the 3 halves, 3 to the n. And we can simplify this. -3 to the n over 3 to the n, that's just the same as -1 to the n over n to the 3 halves. And this converges by the alternating series test. Which means, it converges by the alternating series test because the terms are approaching zero and the terms are alternating. And notice if we put absolute value around it, then it becomes 1 over n to the 3 halves. And this also converges by the p-series test. And so that means it converges absolutely at x equals -3 also. Okay, and so now we can include that left endpoint for where it converges absolutely. Now let's try x equals +3. When we try the right endpoint, we get 1 to infinity, +3 to the n over n to the 3 halves, 3 to the n. 3 to the n over 3 to the n is just 1, so that's the sum from n equals 1 to infinity of 1 over n to the 3 halves. And again, by the p-series test, this converges. Absolutely. It converges whether or not we put absolute value around it. And so our interval of convergence, so now we can say it converges absolutely at both endpoints and throughout the interval. So the interval of convergence is -3 to 3. It doesn't converge conditionally anywhere. And our radius of convergence is r equals 3. Again, because on the number line, if you went from -3 to +3, the middle is 0. We can go 3 in each direction from the center. So you can imagine a circle with a radius of 3 that would go through those 2 points. Okay, for the next example, we're going to find the interval of convergence and then also write an expression for the sum. And so far, the only series that we have been able to write the sum is when it's a geometric series. And so all these are with these directions. When it says write an expression for the sum, it has to be geometric in order for that to work. And so if we expand a couple of terms here, it'll be easier to figure out what our common ratio is. This is geometric. When you plug in 1, we get x plus 1 squared over 9. Then when you plug in 2, you get x plus 1 to the 4th over 9 squared. And then you get x plus 1 to the, when n is 3, that would be 6th power over 9 cubed, and so on and so on. So we can see this is geometric with a common ratio of x plus 1 squared over 9. So each term, to get from one term to the next, we're multiplying by x plus 1 squared over 9. Now we need to write an expression for the sum. And so remember, for an infinite geometric series, the sum is the first term over 1 minus the common ratio. So our first term is x plus 1 squared over 9. And then we're going to divide by 1 minus x plus 1 squared over 9. Now, this is a complex fraction, so you can simplify this by multiplying both the top and the bottom by 9, because that's our denominator in both the numerator and the denominator. And so that becomes x plus 1 squared over 9 minus x plus 1 squared. And that is the expression for our sum. Okay, go ahead and pause your video and try example B. See if you can follow the same steps that I did in example A. Pause your video and then press play when you're ready to see the solution worked out. Okay, so this is a geometric series with common ratio e to the x minus 4. Because the series, if you expand it, is e to the x minus 4 to the first power, and then e to the x minus 4 to the second power, plus e to the x minus 4 to the third power, and so on. Okay, so since the common ratio is e to the x minus 4, this will converge whenever the common ratio is in between -1 and between -1 and 1. And so that means we want e to the x minus 4 to be in between -1 and 1. Add 4 to everything and you get 3 is less than e to the x is less than 5. And so then that means x would have to be in between the natural log of 3 and the natural log of 5. So I got that by taking the natural log of all three parts. So that's our interval of convergence, is anything between natural log 3 and natural log 5. Interval of convergence is from natural log 3 to natural log 5. I don't think I did that in example A. I didn't write the interval of convergence, so we can go back up and say we want our common ratio to be in between -1 and 1. So that means we want x plus 1 squared to be in between -9 and 9. And something squared is always positive, so that's definitely going to be between 0 and 9. It's impossible for something squared to be negative. But then if we think about what numbers we can square to get answers between 0 and 9, we can square anything between -3 and +3, and we'll get answers that are in between 0 and 9, because even when we square the negatives, they're going to become positive. So if you square anything on this interval, your answer is going to be something between 0 and 9, inclusive. And so then we're going to say x plus 1 has to be in between -3 and +3, which means x has to be in between -4 and 2. So that was our interval of convergence for problem A. We didn't do that originally, so I went back and made sure we got the interval of convergence. So the interval of convergence is from -4 to +2. Okay, so now let's finish up with B to find the sum. The sum is always the first term over 1 minus the common ratio. So our first term is e minus 4, e to the x minus 4, and our then it's 1 minus the common ratio, and our common ratio is also e to the x minus 4. So our sum is e to the x minus 4 over negative e to the x plus 3. Plus 5. Because when I distribute the negative sign here, that becomes plus 4. So I have 1 plus 4 is 5. And so that is our sum, which you could also write as e to the x minus 4 over 5 minus e to the x. That would be algebraically the same thing. So that completes our lesson on finding intervals of convergence, testing endpoints, and there are many good practice problems on page 619, so I would recommend trying as many of those as you can, and try to log in with me during office hours in Convergence if you have questions on those.